my name is Sam Studley, and this is my Physics 1 Lab 4 on oscillation.
Introduction to this lab. The purpose of this lab is to investigate the motion of a spring mass system with the spring moving in an oscillation motion. So for the physical experiment, I use the tracker application to track the position of the spring mass system over a certain time t. For the computational model, I use GlowScript to model an ideal system that follows the ideal conditions, and the goal is to determine if the model follows the energy.
So the fundamental principles of this lab, the first is Newton's second law, which says that the change in momentum over the change in time is the net force. So we can rewrite this as the net force is equal to the force of the spring plus the force of gravity, because those are the individual forces acting in this experiment. And we can rewrite this further as negative k L minus L initial times L hat plus mgy, and these are the spring force and the gravity force in their respective directions. Next, we use the energy principle with the system being the mass, the spring, and the earth, and the surroundings here were nothing, so we can say that delta E systems is the work plus of the surroundings plus the change in temperature. So we can say that the change of the energy of the system is equal to 0, and therefore the kinetic energy plus the change in potential energy of the system and potential gravitational energy is all equal to 0. So here we have the observed motion of the tracker, and as you can see, based on this, it creates an oscillation wave. We know that the object's mass is 0.402 kilograms. The extended length, the stretched length of the spring is 0.7 meters. The initial position, as given by the tracker data, is this vector, and the initial velocity is 0 because it starts from rest. So solving for initial conditions, to find t, we can use the equation 2 pi is the square root of m over k, and we can say that t is the average of 3 periods of the wave, and so that generates 1.61 seconds for average of 1 period time. Then we can say the spring stiffness K is given by 4 pi squared m over t squared. And so using that average time we found, we can plug that into this equation to find the spring constant. And then we can use that to find the relaxed spring length by using the stretched spring minus mg over k, and that gives us 0.056 meters. So our computational model, here we have the mass in the initial position vector and the initial velocity vector, which all we found in the previous slide. Then we have gravity, which is 9.8, the spring constant, which we found, the relaxed spring length, which we also found, and then here's the equations for L, L hat, and spring. Then these are the equations for the system energy, so you have the kinetic energy equation, the gravitational potential energy equation, and the total energy equation. Here we have the gravitational force as a vector, which obviously is 0, negative mg, 0. Then we have the spring force here, the net force, so is the spring force plus gravitational force. Here we have the velocity and position updates, which are derived from Newton's second law, the update position for the spring, and here we have the energy changes, so the changes in the energy based off of the energy systems that we put in earlier. So here's the computational model. This is the x position versus time and the y position versus time. And as you can see, between the experimental data and the model, there are a few discrepancies, which can be accounted for that the system in real life isn't isolated, so there is work done by the surroundings. And there's also, I could have been inaccurate when placing my center of mass on the tracker application. So is the energy principle satisfied? So yes, it is satisfied. It is an isolated system, and so there are a few external forces that affect it, but the change in energy is 0, which you can see in this graph, as that delta E line is basically 0. And there's different types of energy change shown in the graph, however, overall it is 0. And so comparing oscillation periods in the x direction, we found, this was on the calculation from the previous slide, that was the spring constant for the x direction of the spring. So that would be this graph here. And however, in the y direction, if we do the same calculation and we find the oscillation period based on the y direction graph, we actually find that it has a greater spring constant. And so choosing different directions for the calculation produces differences in the period time, and this can affect the spring constant k, which overall affects the outcome of the data.
So, an introduction to this lab, the purpose of this lab is to investigate the motion of a spring mass system with the spring moving in an oscillation motion. So, for the physical experiment, I use the tracker application to track the position of the spring mass system over a certain time t. For the computational model, I use GlowScript to model an ideal system that follows the ideal conditions, and the goal is to determine if the model follows the energy